I want to talk more about context-free grammars, and I want to talk about the context-free grammars. As we mentioned last time, they're allow for recursive definitions of them. And one of the things about the languages when we talk about context-free grammars is that they are associated with a machine specifically. Just like you have regular languages, where you have regular expressions, which are the written out format for things that are accepted by a DFA, you have that parallel machine which accepts them as well. And that machine is called a push-down automata. And it can be shown, and we'll show one way of how to do this, but it can be shown that if you have a context-free grammar, then there exists a PDA which will recognize it. Similarly, if there exists a PDA, then there exists a context-free grammar that will recognize it as well. So any language which can be recognized by a PDA can also be recognized by a CFG. Any language which can be recognized by a CFG can also be recognized by a PDA. It's important to have this parallel because the PDA is the process by which we would step through this. So now one of the things that makes that's interesting about a PDA is that the PDA is essentially a non-deterministic finite automata, or an NFA, with a stack associated with it. Now, it's really important that it be an NFA. This is unfortunate for a couple reasons. One of them is that the main reason why this is unfortunate is because you cannot physically build a non-deterministic machine. You can emulate a non-deterministic machine, but you cannot actually build a non-deterministic machine. Because if I have an NFA, and let's talk about not converting it to a DFA, let's talk about a raw NFA, and I have on here this is an NFA. From your start state, you have an NFA ability to go left or right on an A. You can also, if you see a B, you go down. If you see another A from here, you go left. And if you see an A or a B, you go down to the trap state where you self-loop forever and die. You cannot physically build this machine as specified. And you cannot build this as specified because it requires you to simultaneously try both of those. Now, I can make a DFA which accepts this, and it's very easy for me to make a DFA which accepts this, which accepts a corresponding language, but this actual machine, as drawn up here, is not physically realizable. I have to make a change to it in order to be able to realize it. Does that make sense? Because machines cannot try both of them simultaneously. Sean, you look unconvinced.
No.
Okay. So when I talk about a PDA, and one of the things that we talked about, sorry, going back for a second, when I talked about a DFA, we proved via showing that the process that you could take an NFA and turn it into a DFA, that you can always take an NFA and turn it into a DFA. And I gave you a process for doing that. With PDAs, that is not true. PDAs must be non-deterministic. Does anyone have an idea of why PDAs require non-determinism as opposed to DFAs? We went through this a little bit last class.
Something about how with DFAs don't support epsilon transitions, so they don't support getting to...
Well, we can always make a corresponding DFA for every NFA that's out there. So I can make a DFA which accepts the same language. With PDAs, the heart of them is a non-deterministic machine. I cannot create a deterministic term. I cannot guarantee that for some languages, for some languages, to build a PDA which accepts that language will require a non-deterministic machine. Does anyone have an idea of why there are some languages out there that would require that?
Reusing terms that mean different things in different contexts.
It's sort of. It comes down to what we talked about last class, which is that there are some some languages that are inherently ambiguous. Whenever you have an ambiguous grammar, the PDA which accepts that language must be non-deterministic, because it does not know which way it should go. So, and I'm starting at a high level and we'll get down to specifics of how to actually build a PDA soon. But let's look at one language here, where I have, what?
So, for all the ambiguous grammar, the PDA doesn't determine.
If you have a grammar if you have a language that is inherently ambiguous, I'll give you one of those in a second, but there's no way to create a grammar for it that's unambiguous, then the PDA which accepts that will require to be non-deterministic. It's a perfectly valid grammar, but it requires a non-deterministic system. This is the reason why this requiring non-determinism is one of the reasons why PDAs are not used that frequently. In fact, when we talk, one of the topics I have to skip over for lack of time this class is how to create specific types of grammars that do not require non-determinism. Because remember, compilation engines that we talked about last time use context-free grammars to create sentences about how words relate to each other. You can't have a compiler that's requiring ambiguousness. It has to compile. You write code, you want to compile the same way every time. I press build, 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 build. It should build me the same thing every time. It needs to be consistent in terms of how it's done. There's two types of grammars called LR1 and LR2, and they're styles of creating grammars that can be built deterministically. And we haven't covered how to do that. Nor do I think we'll have time to cover how to do that, unfortunately. If you want to learn more, take programming languages, and we'll cover them extensively in there.
So just since you're using deterministic so much, I want to make sure I'm clear with the definition. So deterministic means that it doesn't try a specific point, it tries all available.
No, deterministic means that, it's the opposite. Yeah, it's the opposite of that.
Non-deterministic is what
Yeah.
I mean.
Yes. Non-determinism means that it simultaneously tries all possible options for a given input.
Yeah, that's still hard to wrap my head around.
Well, that's because it's impossible. If non-determinism seems weird, it's because you can't actually ever build a machine that's non-deterministic.
Okay.
So it should seem weird because you can't build it. And that's the point, and that's the reason why PDAs have limited viability. Now, it's important to talk about them from a theoretical point of view because you need to see what they are. But they're limited in terms of utility because they are non-deterministic. So let's look at a grammar quickly that's inherently ambiguous. So the language I'm talking about here is A to the M, and it's unfortunate that I'm using this, so bear with me for 1 second. A to the M, B to the N, C to the L, where either M equals N or N equals L. A, B, and C are terminals, so let's draw our sigma for this is A, B, and C. Those are our alphabets. The M, N, and L here are referring to the number of letters number of repetitions of that. So here would be a string that would be valid as part of it. A, B, B, C, 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 C. this is a perfectly valid string. Because the number of A's and the number of B's are the same, and then we can have as many C's as we want. Similarly, another input here would be A, B, C. This is valid because I have the same number of A's, I have the same number of B's and C's. I'll write up the grammar for this in a second, but I want to point out this language is inherently ambiguous. There's actually no way for me to create an unambiguous grammar for this language. And the reason why is because you don't know when you're creating the grammar, when you see an A at the beginning here, is that A going to match up with the B's, or can I have as many of them as I want to? And it creates a situation where it could be either one of them. And so you need non-determinism, basically like, let's try both and see which one works. And that's what non-determinism does. So let me build up the grammar for this very quickly.
So ambiguous grammar will commonly involve logical disjunctions.
Sometimes. Or they can involve things that just don't. They often involve you sort of subtly making choices. Like the other day we saw the language that about addition and multiplication. That it was sort of a choice of, you can break it up into multiple ways.
Okay.
Now this is inherently ambiguous ones, will often have this sort of thing that can be this or this. And you don't often see inherently ambiguous languages too often in the wild, because the main place where we use context-free languages is in compilers. And when compilers write their language, they write them to avoid specifically being inherently ambiguous because they want them to be compilable, and they don't want to have a non-deterministic machine required to compile code. So it's the reason why you'll see parentheses matching and not something like this, which would be like crazy parentheses matching. And so on that note, let's actually write up, so I'm going to write up two grammars. The first one, I'll write up one first for parentheses matching. Parentheses matching is the language, parentheses, and I apologize for my parentheses looking like C's. Parentheses to the M, and parentheses to the M, where M is greater than or equal to 0. Okay? So, my start variable, which I will creatively label S. My start label will go to, my start label will go to one of two things. It'll either go to another variable P, or it'll go to a variable epsilon. No. Epsilon. There we go.
It's P.
What? P is a variable that I haven't defined yet. P will go to one of two things. P will either go to left and right parentheses, or it'll go to left parentheses, P, right parentheses.
Does epsilon represent going to the start state? Or
Epsilon means nothing. It means nothing string here.
Okay, so, right, I see.
So let's create the parse tree for two parentheses. You start at the start. Start goes to P. P goes to left parentheses, right parentheses, P. This P then goes to left parentheses, right parentheses. This language is unambiguous. This grammar is unambiguous. There's only one way to create a parse tree for any given set of parentheses. I had to include the epsilon here because this is greater than or equal to 0. because it's possible for you to have an empty string. If at all possible when you're writing grammars, I highly recommend you include epsilon only as an option on the very top, if at all possible. Because it's only to show that you are accepting the empty string. Trust me on this, your life will be made a lot better. It will dramatically decrease your mistakes if you keep epsilon contained to one of the options on the very highest level. It is very, very, very easy to make mistakes when you start putting epsilon in grammars you're writing lower.
In the parse tree, why couldn't P just go to the left parentheses?
Because that would not represent that.
Oh, it's parentheses.
Yeah.
Okay.
It could, but that would be a different string, and it would not be a valid parse tree that would accept this string. That's a great question, because you can have these options. So it says for a given string, when you look at the terminals from left to right, and for across the entire parse tree, that exactly matches that. And there's only one tree that matches for that. Rob, did you have a question? Or?
It doesn't have to be left to right, is it? That's just like convention.
What?
Like when reading it, like, so if you had right parentheses, then left, then left, that would still be the same, right?
No, that would not be accepted by this.
Oh.
Yeah, that wouldn't be accepted by this language, because this implies that you have m in a row followed by another m in a row. If I wanted to denote that, how would I write that up? I would write that up by saying that grammar, and I'll write this up in red to show I'm not actually doing it. I'll write up in the crappy red marker that's dying. So I would write that one up like this. Oh god, I need parentheses. Let's add square brackets. So that's how I would write up mixing between the two. Wow. And then you actually have the bar here, which is not that bar. I want to be clear about that. That's an or. That's a such that. Let's just throw an epsilon in there for good measure. Doesn't do anything. Just put those everywhere, actually. There we go. Now it's far more confusing. It does nothing different.
Your left squiggly brackets are like almost perfect epsilons.
Except
Your
bigger.
right ones are actually just squiggles.
Yeah. Funny how that works out, isn't it? It could be zetas. Lowercase zeta.
It's more like a sideways bird.
You'll notice that I never write a lowercase zeta. I cannot write them at all. And that's saying something, given that I apparently can't write right squiggles either. Okay, so does this make sense why this is this grammar? So let's create the far more complicated grammar of this. So this grammar is going to have, it's going to be inherently ambiguous as well. What we're going to have here is we have the possibility that there's going to basically be two things that can be going on here. One is we have the same number of A's and B's, and another one is the same number of B's and C's. So at my top level, I'm going to create, it's going to basically have an OR of which of these two options is it going to go to. And that OR is going to say, that OR is going to have the letters, what letters? Let's do X or Y. X is going to denote where there's the same number of A's and B's, and Y will denote where there's the same number of B's and C's. So X is going to go to one of two things. It's going to go to a variable DC. This D variable will represent a matched number of A's and B's. This C variable will represent as many C's as I want to. Now I know I told you to put epsilon in the highest level there. Generally you want to do that. I'm not going to put it in the highest level here, simply because it's going to make our life a lot. In this case, it is a little bit easier to put it a little bit lower than that. So let's do the C first, because that's going to be a lot easier. So we want to have as many C's. We want to have 0 to infinity C's as we want to. So I will write that out by saying you can go to, you have uppercase C, left parentheses, uppercase C, which is for cookie. But
Your C's look like what?
that's why I wrote cookie in there, so you know it's a cookie.
Your left they actually look like C's.
So that's a C.
How do I make it more like, I don't know, just make them G's. I'll make it a crescent moon. There you go.
That's a left fruits.
That's a C. D or J? J.
They're giving him a hard time.
I was confused.
Yeah. You know, let's actually go through here. I'm going to make a requirement that'll make our life a little bit easier and make M greater than or equal to 1, N greater than or equal to 1, L greater than or equal to 1. I don't want to have to worry about empty strings. I'm going to cheat and make our life easier that way. So, J can go to the letter C or CJ. Okay? D, on the other hand, can go to AB or ADB. Note, I want to point out a really interesting part about that's in both of these languages. Notice that I have the variable in between the two. This is an important property of context-free grammars, which is that they can recurse, but if you want to make matching on the same number of sides, or you want to have information conveyed about the left-hand side to the right-hand side, you put the variable in the middle. If you want to have an recursion of an arbitrary depth, and you don't really care about that information, then you have one terminal, or a series of terminals, followed by a variable on either the right or the left-hand side. And this is an important part about how context-free grammars work, is that every time I go down D here, I have to add another 2 levels of A and B's. So this will guarantee that my A's and B's are matching. If I were to have another D over here, I would not necessarily have this guarantee that the number of D things in here matches with the number of D's that come out of here, because they're 2 separate variables. If I need to require it, I need to have it all in the same statement. And typically, it's you grow from the middle. Does that make sense? That's what happened here. We're actually growing the parentheses from the middle here. Same thing here, we're growing the A's and B's from the middle of them. So, this is the grammar for if we have the same number of A's and B's. Let's write the grammar now for we have the same number of B's and C's. That grammar, Y goes to E, K. E will represent as many A's as we want. K will represent a matched numbers of B's and C's. So E will go to A or A, E. K will go to B, C, or B, K, C. Any questions about this so far?
So basically, you can create A, B, and
So-
two separate ways, so the language is.
Well, I'll show you. I'll show you one example where I'll show you the example where it's ambiguous right now. So this is inherently ambiguous because I guess I'll have to write it over here. How do we create the parse tree for the string A, B, B, C, C? So A, B, B, C, C. What's the parse tree that accepts that? There's actually going to be two parse trees that accept this. In fact, however you write this grammar, this is one way of writing the grammar. I could write it up several different ways. No matter how I write this grammar, this string A, B, B, C, C will always be ambiguous. And the reason why is because there's two ways I can accept this string. I could accept it because A and B's are equal, or I could accept it because B and C's are equal. It's valid twice. There's inherent ambiguousness in this. And because of that, we have to use the NFA in order to accept this both different ways. Or not NFA, non-deterministic PDA. So let's go through the parse trees for this. So, parse tree 1, the parse tree family. I'm sorry. So S goes to X. X goes to DJ. D goes to A, D, B. D goes to A, B. J goes to C, J. J goes to C.
Is that a D after X? X is
X goes to D, J. I should mention, the first time I taught theory, I did it all without slides. Because I thought, it's a theoretical class, we should get the computers out of here. That did not go as well as I anticipated. My handwriting is apparently not as good as anyone else on this planet. Fun time. Okay, so this is one parse tree. Another parse tree we can do, S can go to Y. Y can go to E, K. E can go to A. E can go to A. K can go to B, K, C. K can go to B, C. Any questions about that? So as I mentioned, this is what's called an inherently ambiguous language, because no matter how I write this, it's going to have two different parse trees to accept it, at a minimum. I could write context-free grammars that are even more ambiguous than if I so choose, but that seems really silly. As a result of this, it's going to require a non-deterministic machine to be able to accept it. But it's a perfectly valid grammar. Any questions about this before I go on and do some more stuff with PDAs? So let's formally define PDAs then. So a formal definition of a PDA is the sixth tuple. And this should look familiar to you from the, we talked about this with DFAs and NFAs. We have a set of states, the input alphabet. We have another alphabet here, which is the stack alphabet, because we can have additional symbols on the stack that do not occur on the input tape, on the input originally. This will include all of our variables. So the stack alphabet here is the combination of everything which is in the input alphabet plus all of the variables. We then have our delta transition function, which goes from whatever state you're currently in, crossed with whatever you're currently reading from the input, crossed with whatever at the top of the stack, will go to, again, it's non-deterministic, the power set of states with a new thing on the stack. We have a start state, and then we have the set of accept states as well. Recall that for NFAs, the big difference here is once we didn't have a style alphabet. We also, it was like this. We didn't have a stack that we were putting elements on, and we didn't have a stack that we didn't have a stack that we were popping off, we didn't have a stack we were pushing on. And that's what this will represent. This represents pop something off the stack. This represents push something onto the stack. You guys know if I go on? So, we're going to show how to build a PDA from a context-free language. But before I get to that, I want to give you guys a heads up with how the notation of this is going to look. So, what we'll have here is we're going to have, so I'm going to formally build a PDA, show you the whole formal process for building a PDA from a context-free language. But before I do that, I want to show you my eyeballing of how I would build this. I'll show you the formal process for taking this grammar and turning it into something soon. But right now, I just want to show you the eyeball approach to it because I've done this a few times, and it's a little bit easier to see it first in the more simplistic way before you go to the full algorithm. So, a PDA has a start state. From the start state, what happens is and I want to just make sure. Before on NFAs, you'd only see one thing on here. So you'd see something like left parentheses, right? Well, now you don't just see left parentheses. You see what's on the tape will be three things. What's read off the tape, what's read off your input, the thing that's on the top of the stack and is being popped off. And I will call this Q. I could call it literally anything I want to, but I'm calling it Q. Because Q is a fun letter to say.
And like John Delancey.
No, but Q is kind of funny because it's going onto a stack, so it creates a weird pun.
That was actually pretty great.
Yeah. John Delancey, that's...
To play Q.
Oh, okay, sorry. I was like, I know his name. I'm blanking on it. I would call it a Q because it's referring to... I was thinking about a different type of Q. I was thinking about the fact that the word Q and that Q is being pushed onto a stack. Sorry, I was going for a different type of joke entirely, but well played. But we're not actually we're not actually popping anything off the stack yet. You'll see, instead what we're going to do is we're going to say, what do you see at the top of the stack? Well, I see nothing at the top of the stack. So I'm going to pop off nothing. I don't care right now if I'm popping anything off. And so that's what epsilon will represent. I will then push onto the top of the stack the letter Q. So read from input, read and pop off of the stack. If you're not reading and popping off, you put an epsilon, and then push onto the stack. I'm now going to self loop. Here, where I keep on reading left parentheses. I'm reading nothing off the stack, and I keep pushing Q's on. Eventually, I'll see a right parentheses. When I see a right parentheses, what I'll do is I'll examine the top of the stack. I will pop off, if I see the letter Q, I will pop it off. And then I will push nothing onto the stack. It is possible to both push and pop something simultaneously onto the stack. Sometimes if you want to see what's on the top of the stack and don't want to progress down that way, you'll push and pop. And then this will go to a self loop where I keep on pushing and popping. I keep on popping epsilons off of the stack.
Wait, isn't that pushing?
This is popping Q's off of the stack and pushing epsilons, which are nothing.
So basically, you're expressing that continually adding these extra parentheses doesn't take anything off the stack, so you can do it indefinitely.
So what's happening here is that, so this is not quite done yet. We actually have a few more things we'll have to add to this. Most notably, we're going to have to add except states. And the way this is drawn right now is actually insufficient for exactly capturing this. We have to add one more thing, which is super annoying. So what happens here is that on a DFA or an NFA, you saw what was on your input. You kept track of where you were on the input, and that would take you to a new transition. What's happening here is you have to actually check two things. One is what's on the input and what's on the top of the stack. Just like with NFAs, epsilons are free. There's always an epsilon on the top of the stack, and similarly, there's actually always an epsilon at your current input, on your current place in input. But you get to certain places like right here. You cannot go down this route if you do not see a right parentheses and a Q on the stack. You have to have both of those in order to make that traversal. When you go down this traversal, it has the side effect of removing Q from the stack and replacing it with, in this case, nothing, or whatever the transformation was.
So that Q stands for
The number of parentheses that are on
the
there.
number.
So, the reason why this will not work is because we have no way to tell if our stack, the way this is written, we have no way to tell if the stack is empty. We have no way to tell if we've exhausted our queues. So the temptation would be to make this the except state. But that won't work because then that would accept any number of left parentheses as long as there was just one right parentheses. You can think, okay, then maybe we'll have another thing here, epsilon, epsilon. So there's nothing on the input, nothing on top of the stack. That takes us to an except state. That also won't work because there's always an epsilon on the input and there's always an input on the stack. So we have to do this annoying thing, which is we have to put a marker on the bottom to denote we are at the bottom of the stack. And we have to do that initially. So the first thing we do, we actually make another state here to begin with. And our start state, the first thing it does is it sees an epsilon on the input, so it consumes no input. It sees an epsilon on the stack, so it consumes nothing off the stack. And it pushes on a symbol on there, which denotes the end of days. And I will make that symbol a smiley face. It literally could be any variable you want. I always like making a smiley face or a lightning bolt just because theoretically I can do that, and I'm in theory, so I'm fucking doing it. So what we do here is now at the end, we consume an epsilon off of our input. we consume our smiley face off of the stack, and we push on epsilon, and that moves us to an accept state. And we actually did it because you can have 0 parentheses, that's also an accept state. So let's go through this. So I'm going to do left, 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 right, right, right. That's our input. And I'm going to draw input, stack. Okay. So we start off here, left parentheses. Well, we have to make a move. We see epsilon on the input, epsilon on the stack. So we have to follow this transition because we have to consume this character. So we move over there and we're like, okay, the pointer on there doesn't increase. Nothing gets removed off of the stack, but what happens is we push the smiley face onto the stack. Now we're at this state. Now what we do is we see a left parentheses. Hey, we have a left parentheses in the input. We consume, we don't look at our stack at all because there's an epsilon there. And then we advance that one character off of the input, move our state to here, and push a Q onto the stack. Now we're up here, we're looking at this parentheses. What do we see on our stack? Well, we see a Q on the top of our stack. Can we take this transition?
No.
Right, there's not a right parentheses. We're still at the left parentheses. So we have to go down this route. Left parentheses, epsilon Q. Does everyone see why that's the case? You have to match with both of them. We do match with the stack over here, but we don't match with the input. So we match with the input. We get the freebie match card in the stack. We take this transition. We move our input up by 1. We push Q onto the stack. And we go forward. Now we're at this state. We're here. Again, we see a left parentheses, nothing on the stack. We're doing nothing on the stack. And we push a Q on as well. And now we're at the right parentheses. At the right parentheses, hey, we don't see any more left parentheses. The epsilon is actually still true, but we don't see left parentheses, so we can't take that transition. So we have to take this right parentheses, Q, go forward. Okay. So as part of examining the Q, we replace it with epsilon. Whoop. Wonk, wonk. And we move our input ahead by 1. We're now in this state. We now consume another right parentheses in Q. And we move our cursor 1 more, another right parenthesis in Q. And now we're in the place where we see epsilon on the input, so whatever we went to on the input, and smiley face on the stack. Hey, smiley face is on the stack. Huzzah! We move to our accept and remove smiley face off the stack. The reason why we needed the smiley face, consider what would have happened if we had had 3 on the left and 4 on the right. Actually, sorry, 3 on the left, 2 on the right. So we come here, and we push, let's say we push the smiley face on, we have our Q, 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 we come down here, we pop off a Q, we advance our cursor 1, we pop off our Q, advance our cursor again. Now the cursor is at this point. We are in this state. What option do we have?
Absolutely nothing.
There's absolutely nothing we can do, which means we fail. Because if there's no matching for the system, just like with NFAs, if there's no match there, you assume you go to the null state. What? You always assume that if there's no match from the state from where you are, then you're dead. So.
Null state.
Yep, the null state.
Null state.
No, the null state. Oh, the hell state, yeah. Oh, I thought you said how. And I'm like, oh, no. So does that make sense? And that's what smiley face guarantees, is that the stack will actually be empty, which means you've actually successfully matched your left and right parentheses.
So there's always epsilon on the stack.
There's always epsilon on the stack, and there's always epsilon on the input. Epsilon off the stack doesn't consume anything from the stack. Epsilon off the input doesn't consume any letters on the input.
Epsilon is just the theoretical,
It just-
blank spot at the top, right?
It just means ignore the space. It's like, it's the wild card. It means it consumes nothing. It means, basically it's a wild card. It means, oh, just as long as you match in the left parentheses, that's fine. Just as long as you match in the stack, you're fine.
See, because it seems like you're, each time what you're doing is saying, okay, I put on, or I take off the left parentheses, I turn the epsilon at the top of the stack into a Q, and do that,
Yes.
and then turn
Yes,
Q at the top of the stack to epsilon.
yes, that's exactly what's happening. Cool. Don't forget, you guys have an assignment to do